Hey everyone! In this video, I would like to talk to you about recursions, which offer a different approach to solving problems compared to traditional imperative techniques using loops and mutating variables. Today we'll compare these two approaches across a few realistic examples, and we'll discuss how to encode and work with enumerations in Scala. Are you ready? Great! So it's important to mention that there are different kinds of recursions. We can have recursive data structures or recursive algorithms. But the idea behind them is the same: a piece of code that references itself. Let's see what this means in practice. First, let's talk about recursive functions. Here I've defined a function called printMany, which takes two arguments: n, an integer that represents how many times we want to print a text, and message, the actual content to be displayed. So if we call printMany with 3 and fp is awesome, we'll see the phrase fp is awesome written 3 times in the standard output. As you can see, printMany is recursive because it calls itself when n is larger than 0. And since we don't want this code to loop forever, we decrement n by 1 at every recursive call. This way it will eventually terminate when n reaches 0. Note that we could have done exactly the same thing using a variable named counter and a while loop. The loop iterates as long as counter is positive, and in the body of the loop we decrement this variable and print the message to the command line. With a little refactoring, the similarity between these two implementations is even more visible, and it's up for debate which version is the most readable. To be honest, I don't think either is particularly great. In that scenario, I would probably prefer using for each over a range from 1 to n. Either way, the most important takeaway is that recursive functions and imperative loops are both ways of repeating an action until certain conditions are met. Now, the most common use case for recursive functions is to work with recursive data structures. So let's have a look at a few examples. Here I define a case class called person with two fields, name and children. Person is recursive because its field children also refers to an instance of the person class. This makes sense because a person may have children, who are in turn persons, who may also have their own children, and so on. A similar relationship exists between companies and their subsidiaries. In fact, we work with recursive data structures almost every day without even noticing it. For example, JSON, YAML, or XML. Pretty much all serialization formats are recursive. Take this JSON document. It's an object with a key name that maps to the string John Doe, a key age that maps to the number 25, and a key address that is itself a JSON object. A good way to visualize this is to see a JSON document like a tree, where the leaves are either numbers or strings, and the branches are JSON objects. There are other kinds of JSON values, but we'll ignore them for now. So the question is, how do we represent a JSON document in Scala? Could we say it's a case class with 3 fields, a double, a string, and a map string to JSON? Not really, because a JSON is either a double, a string, or a map, but it cannot be those 3 things at the same time, can it? Then what if we wrap every field in an option? Then we could define a JSON string by setting the text field with a sum John Doe, and the number and object fields with none. Yeah, that would work. However, there is still nothing that constrains the JSON class to a single field with a sum, as you can see with these two examples. So a case class is not a good fit when you want to encode a type to be either this or that, but not both. Instead, what we need is an enumeration. This is something I've mentioned in previous videos, though I've not yet shown you how to define one. So let's do that now. In Scala, we define an enumeration using the keyword enum, followed by the name we want to give for this enumeration. Then in curly brackets, we mention each possible case. Case JSON number, which contains a double, case JSON string, which contains a string, and finally case JSON object, which wraps a map string to JSON. And it is this final case that makes JSON recursive. Now with this encoding, we can create JSON values using json.jsonnumber, or we can import json._, so that we get all three constructors in scope. Actually, I did mislead you a little, because this syntax for an enumeration is only available in Scala 3. If you're using Scala 2, as we are for this course, we'll need to write a more verbose solution. Instead of using enum, we'll say that JSON is a sealed trait, and then each case of the enumeration will be a separate class that extends the JSON trait. Here the keyword sealed is crucial. When the compiler says this, it verifies that all classes that extend the trait are defined in the same file. So we can say that a sealed trait is an enumeration because we are technically forced to create all these classes together. If you're using Scala 3, you can use both syntaxes. In fact, when the compiler encounters an enum, it actually handles it by generating the corresponding sealed trait automatically. So that's why it's important to understand how a sealed trait works. It explains why we can use JSON number, JSON string, or JSON object to create JSON values. Each case of the enumeration is a class of its own. So when we write JSON number 12, we create an instance of the type JSON number, and since JSON number extends JSON, this means that the value is also of type JSON. Does that make sense? Great. So let's try to implement some functions that work with JSON values. Imagine we store some records in our database in the JSON format, a user profile, for example. And let's say that we discovered that for the last couple of months, the form that captures a user's data wasn't trimmed, which means that we may have leading or trailing white spaces anywhere inside the user record. So how could we remove that? Let's define a function called trimAll that takes a JSON and returns another JSON. Then because JSON is an enumeration, we can pattern match on it, and the compiler will verify that we handle all the possible cases. For example, if we forgot to consider the case where JSON is a string, then we would get a warning telling us that the match may not be exhaustive. And if we use a recent version of Scala, we can even transform this warning into an error using this compiler option. Cool. Now what do we do if JSON is a number? Well, there is nothing to trim in a number, so we need to return a new JSON number with the same value. Good practice in this situation is to use an underscore before JSON number, so that we don't even name this branch of the match, and return the input of the method unchanged. Then if JSON is a string, we trim the text inside it. Finally, if JSON is an object, we recursively apply trimAll on every JSON value in the map. In this case, the keys will stay unchanged. Now if we call trimAll on our test user John, we see that both its email and postcode were trimmed, even if those fields are different levels inside the JSON document. Great. So now it's your turn to practice working with JSON documents. Please open the file jasonexercises.scala in your favorite IDE. First, we're going to implement anonymize, a function that takes a JSON value and removes all the sensitive data. This means that all strings will be replaced by 3 asterisks and all numbers by 0. For example, if we get this JSON document encoding a user, anonymize conserves the structure of the document, but all the user's data has been blanked out. Cool. So can you please pause the video and now try to implement anonymize recursively. Okay, so because anonymize takes a JSON and JSON is an enumeration, almost the best thing to do in every case is to do a pattern match on this. Because JSON is a relatively complex data structure, but when we do a pattern match, we go from one complex problem to 3 simple ones, which is generally better. So what do we do now if JSON is a JSON number? Well, we want to return a new JSON number, but this time with 0, hard-coded. If it's a JSON string, we want to return a new string, but this time with 3 asterisks. And if it's an object, we want to keep the keys unchanged, and we want to apply recursively anonymize on every single value. So we'll create a new JSON object, because anonymize never change the type of JSON. It just blanks out the data. We have obj, so we'll map it. And as you can see, map takes an update function that as an input, it's a tuple string to JSON, and it returns a tuple key value where key value are completely parametric. So in our case, we're not going to change the type. We'll say map. We'll pattern match on the key value, on the tuple. So it's a key value. The key will stay unchanged, so we keep it like this. And the value we'll call anonymize on it. Quite simple, isn't it? Now, a small refactoring. We can see that text and number are both grayed out. This is because we don't care about them. Anyway, the transformation is hard-coded. So the good pattern in this case is to use an underscore instead to make it clear that these values are useless. Now let's run the test. We can go to the file JSON exercises test. I wrote a couple of unit tests. Most of them are ignored at the moment because the functions were unimplemented. So let's replace ignore by test, and let's run the test suite. So we can see that trim all and anonymize pass, but search and depth are currently ignored. So what did we run? So the input, we took John and we anonymized it. So what is John? It's a JSON object with a name, age, and address, street number, and street name. So it has various strings and numbers. And if we look at the result here, all the strings are triple asterisks, and all numbers are zeros. So it's exactly what we want. Cool. So let's go to the second exercise, where we are going to implement search. It's a function that tries to find if a string is present inside the JSON document. The match doesn't need to be exact. For example, if we search for LL, and the JSON contains hello, then it will be considered a match. Also, search should only check for values in a JSON object, meaning that keys are ignored. So can you please pause the video and have a go at implementing search? Okay, so by now you start to know the drill. Because search is a function that takes an enumeration, we start by an exhaustive pattern match. What happens if the JSON is a JSON number? Well, in that case, we know that we'll never find a matching string within a JSON number, so it's always going to return false, isn't it? Then if it's a JSON string, we need to verify if this text contains this one. They do have the same variable, so it's going to be a problem. So let's rename one of them. Maybe let's call it search text to make it a bit more clear. So here we'll verify that text contains search text. This contains, let's double check the doc, returns true if and only if the string contains a specified sequence of char values. So I believe that this works if it is anywhere within the string. We can verify as a unit test. And then for JSON object, what we want to do is to look at all the values inside the JSON object. So this gives us an iterable of JSON. And we want to find if any of these JSON value contains search text. If any of them has it, then we return true, that's okay. If none of them has it, then we will return false. So what we could do is do map. So this will give us access to the value inside the map. Then we want to call it recursively, so we want to say search. We want to search the value with the same text. Okay. So now we have an iterable of Boolean, and we want to verify that at least one of these Boolean is true. So there is a higher order functions to verify if at least one thing is true. It's called exists. So exists takes a predicate function, and the input is the data inside of the collection, so it's a Boolean. And you return a Boolean. So in our case, it's the same thing. So we'll say, if the Boolean is true, then that's it. So this is kind of the identity function, so we could refactor it. But in fact, something better is that instead of calling map and then checking to exist, we could have straight away checked that use exist. Because this way we say, okay, I have an iterable of JSON. Could you please verify that any of these JSON contains this text, which is exactly what we want. If you really want to make it shorter, which is not necessarily better, you can use also an underscore like this. And here, in this case, it is a good pattern to use an underscore to make it clear we don't care. Okay, so let's run the unit test. So let's set it to test, replace ignore by test, and let's run them. Cool, so they all pass. Let's have a look at what we did run. So we have different kind of JSON as an input, like a JSON object that is empty, a JSON number, a JSON string. And we verify, for example, like if the search text is a substring of this one, then it matches. So we were not entirely sure about content, so it does actually work as we expect. Great. Now, last exercise for JSON, it's called depth. So the idea behind this is we take a JSON again as an input, and we want to calculate how deep is this data structure. And how do we define the depth of a JSON? We say if it's a JSON object but it's empty, then or a JSON number or a JSON string, then it's 0. Then if it's a JSON string with any kind of value inside it, it has depth 1. And if it's a JSON string which has, again, another JSON object inside it, then we kind of apply the same process. Like if any child is a JSON object with some data, we do +1. Cool. So I'll let you pause the video and try to play with it. Okay, so for depth, again, it takes an enumeration, so we start always the same with an exhaustive pattern match. So what do we do if it's a JSON number? If a JSON number or a JSON string, we return 0. So in both cases, it's going to be 0. Now, if it's a JSON object, this is where it's a bit more complex, because it says if it's a JSON object but it's empty, then it's also 0. So we can say if obj being the map inside it is empty, then we return 0. Otherwise, what do we want to do? Well, we want to calculate the depth of every single child. So we'll say obj.values. This will give us access to every single children. we'll map it and we'll call def on this value. So this will give us an iterable of int, meaning that this will be kind of a collection of the def of every single child. What we want to do in this case is to look at the biggest of these values, because imagine if you have a JSON with two children, one that has def 1 and one that has def 5. We want to take the one that has def 5. We don't really care about the branch that is the smallest. So how do you get the max value? You can use, there are actually two functions, max and max option. So max is is dangerous because if the iterable is empty, then it will return an exception. In itself, here we are pretty safe because we already checked the map is not empty. But still, I think max is quite dangerous. Sometime in the future may refactor this code, and then this code will start to blow up. So generally speaking, I think it's better to use max option because this will return an option of int, and in case the object is empty, we'll have a none, which means we can pattern match again on this. So here we have two cases. If it's none, then it's 0, which means that we can actually get rid of this if then else, because here we're already considering the case where object is empty. And this, if we have a data, if we have some value, what is it? It's the max depth, or the depth of the biggest child, the deepest child at least. So what do we want to do to this is that we want to return max depth plus 1, because if our child has a depth 3, we will have a depth 4 because we are one level higher here in this JSON object. Does that make sense? Cool. So I think it's quite neat. We can do a couple of refactorings here. We can remove the value and pass, like do an eta expansion, just map it straight away like this. We can remove number and text because we don't use them. Actually, here we are in a different case than we had before, because both JSON number and JSON string return the same result. We say whatever the kind of JSON number, whatever the data inside of JSON number, or whatever the data inside of JSON string, anyway return 0. So there is another syntax for a case like this. You can say double underscore column, this means like any kind of JSON number, and you can say pipe and say the same, underscore column JSON string. So this way it expresses if the JSON is a JSON number or a JSON string, I don't care about what's inside of both of them, then I return 0, which makes things very clear. And especially convenient when the data here will be more complex. If in this way you don't repeat yourself. Cool, so let's run the test. We'll go to JSON exercises tests, remove the ignore here, and let's run it. All good, so def is successful. Let's have a look at what was the unit test. So we check if the JSON is a JSON number, or if it's a JSON object and the map is empty. In both cases, we return 0. For some kind of JSON object with at least one value, we return 1. And for John, our test user, we return 2, because John has a JSON, it's a JSON object, and within the JSON object, there is another JSON object with a map that is not empty. Great, and as usual, if you're extra motivated, I've added bonus exercises at the bottom of the exercise file. So using this JSON example, we have demonstrated that recursive functions are a convenient way to analyze recursive data structures. So now I would like to cover another example of those structures and use it to compare imperative and recursive approaches to a problem. As I said before, recursive data structures are everywhere. One example is a file system on our computers. A file is either a normal file, such as a Word document, a picture, a video, or it can be a directory, right? But what's inside the directory? Other files, and this can go as deep as we want. For this next example, let's create a new Scala project. You might be aware that SBT offers a templating solution with the command sbtnew, where we only have to specify the name of a repository on GitHub. Here I'm using one called scalaseed.g8 from the official Scala organization. Those templates generally end in .g8 because they were originally made for a tool called Ch03. If you're interested, you can learn more about this feature in the text below the video. Let's say we want to calculate the size of this directory. Using the command line, it's pretty straightforward. We can use the command du, which stands for disk usage. But the question is, how do we do this in Scala? Let's start with an imperative approach. We'll first need to define a function that takes a Java I/O file and returns a long, representing the size in bytes. Then the next step is to differentiate whether the file is a directory or a normal file. If the file class were defined in Scala, it would have most likely been encoded using an enumeration, as we did for JSON. However, files come from Java, which didn't have seal classes until Java 15. So this means we can't pattern match on the input file. Instead, we need to call the method isDirectory and do an if then else. So if it is a normal file, we'll return its length and we are done. But if the file is a directory, we'll need to iterate over all its children and calculate their size. For this, I use a for loop and a mutating variable, as we did in the previous lecture. However, there are two issues with this code. First, a directory in itself takes up some space, even if it's empty. So in both cases, whether a normal file or directory, we should measure the size of the file. The second problem is more difficult. Some of the files within a directory may also be directories, which means that we need to open them, add the size of their children to total, and repeat the process over and over until all directories have been traversed. So there is a recursive pattern here. But first, let's finish the imperative solution so that we can compare the two approaches. The traditional way to tackle this problem imperatively is to define a mutable data structure to store tasks. For example, a queue, and we initialize it with the input file. Then we use a while loop to continuously remove elements from this queue until it's empty. Within the loop, we increment the variable total with the size of the file. And if it is a directory, we add all its children to the queue. Let's visualize how this works. The queue starts with one file, scala-c-project, and total equal to 0. Then we remove the first item from the queue and add its length, 192, to total. And then we check if it's a directory. It is. So we add all its children, .gitignore, build.sbt, project, and src to the queue. And then we process the next item, .gitignore. It's an ordinary file, so we simply add its length to total, and we do the same for build.sbt. Then we encounter project, which is a directory. So we add its length to total, and then we add all its children to the queue. Our program will continue to do this until all files have been processed. Does that make sense? It's certainly not straightforward. We have to be very careful about how we define the variables, the conditions of the loop, and when to remove or add elements to the queue. This is a kind of pattern that years of imperative programming beats into you. It doesn't come naturally. Okay, now let's try to implement disk usage using recursion this time. The function signature will be the same. It takes a file and returns a long. So we start by checking if the file is a directory or a normal file. As with the last time, we can get the file size from its length, though if the file is a directory, we also need to add the disk usage of all its children. So to calculate that, we iterate over all the children and call disk usage recursively on each one of them. This gives us an array of longs because the method listFiles returns an array and disk usage returns a long. Finally, we sum up the entire array using the method sum from array. Nice and concise, isn't it? What I particularly like with the recursive implementation is that it exactly matches how we would explain working out the size of a directory to someone. This is a very common feeling when we deal with recursive structures. The recursive approach naturally fits the problem. In contrast, the imperative implementation is more a step-by-step instruction on how to calculate this size. Take this here, move it there, add to that number, which makes it more error-prone. However, if we look behind the scene, it turns out that these two approaches work in exactly the same way. How is that? Using the imperative approach, we use a mutable queue to store the tasks, while in the recursive implementation, we use a function stack. As you might be aware, every time we perform a method call, it adds a frame on the stack. This frame contains the method's name, its parameters, and all of the internal variables within that method. Let's visualize how the recursive function is executed. We start by calling disk usage on Scala seed project. As you can see, it adds a frame with this file name on the stack. Then, because it's a directory, we call disk usage recursively on its children. First on .gettingNow, which adds a second frame on the stack. .gettingNow is a normal file, which means that after we compute its size, we remove its frame and go back to the Scala seed frame. Then we repeat the same process for build.sbt. When we reach project, this time it is a directory. So we need to call disk usage on all its children, which adds a third frame on the stack. So if we imagine the file system as a tree, where each branch is a directory, shown here in green, and each leaf is a file, shown here in blue, then calculating disk usage recursively requires a stack with a size that is proportional to the depth of the tree, right? This is where we potentially have a problem. The stack is quite small, and if a recursive function calls itself too many times, then boom, we get a Stack Overflow exception. So let's take a quick detour to talk about the JVM memory model. The JVM has two types of memory, the heap and the stack. The heap contains objects, for example, instances of string or any other classes, while the stacks contain frames for each method call. And each frame holds variables and parameters defined in that method. If the variable is a primitive, such as an int or a boolean, then it is stored directly on the stack. And if it's not a primitive, then the stack keeps a reference to the corresponding object on the heap. It's important to note here that in a Java virtual machine, there is only one heap for the entire JVM, but there is one stack assigned per thread. We'll talk more about threads in the next video, but for now the key idea is that a typical application may have dozens or even hundreds of threads running at the same time. This means that the JVM may need to allocate dozens to hundreds of stacks, which is one of the reasons why each stack is much smaller than the heap. A typical stack may have hundreds of kilobytes, while the heap may vary between hundreds of megabytes to dozens of gigabytes. These settings are configurable, but this example is just to give you an idea. All of this is really to say that with recursive functions, we need to be very careful about how many recursive steps occur. We don't have the same problem with imperative implementations because they rely on explicit data structures, such as a queue, which live on the heap where we have much more space available. Does this mean we should favor imperative implementations over recursive ones? Not necessarily. There are a few alternative ways to address this problem. First of all, the problem might only be a theoretical concern. For example, one could argue that in practice, all the JSON documents, file systems, or other kinds of trees that our application manipulates are relatively shallow. So if we never intend to process deep structures, then this problem will not occur. You might find this line of argument a little bit shaky, as although this might be correct right now, we can't necessarily predict how these recursive structures will evolve in the future. For example, we wouldn't want to get a Stack Overflow exception if our application starts to generate more traffic. There is a way to prove that our data structure is shallow. If we force the tree to be balanced, meaning that we don't have big holes in the middle of the tree, like this one, then when the tree is balanced, the number of elements in the tree is exponential. It will be around the average number of children per branch to the power of height of the tree. So in practice, if we have a balanced tree with approximately 2 children per branch, then we know we'll never get a Stack Overflow. This trick is used in the implementation of vector in the standard library. A vector is a tree with up to 32 children per branch, which means that in practice, we'll run out of memory from the heap before a vector reaches tens level deep. This is the power of exponential. It grows extremely fast. That's a very cool property, but we can't always guarantee that the tree is balanced or that the average number of children is larger than 2. In fact, there is an extremely common data structure that doesn't fit these requirements. It's actually the list. Indeed, a list in Scala is a linked list, which means that every element is connected to another one until it reaches nil at the end. So in a sense, a list is a tree with one child per branch. So it's a bit like a bamboo, you could say. We don't usually think about it this way, but it's useful to help us understand how a list can be the worst possible case when it comes to stack safety. Let's have a look at an example. Say we want to implement a function that takes a list of int and then sum all the numbers together. You might recall that we implemented this function with a for loop in the previous lecture. This time, let's implement it using recursions. The first thing we'll do is pattern match on the list to check if it's empty or not. And we can do that because list is an enumeration with only 2 cases. Either it's case nil, meaning that the list is empty, or case double column with a head and a tail. Now this seems like a really weird idea to name a class double column, but that's how it's defined in the standard library in Scala. This is done this way in order to use double column as an infix operator when pattern matching on a list. For example, on the left-hand side, we wrote case head double column tail instead of case double column between parentheses head and tail, as we might have done using the standard syntax for pattern matching on enumeration. So if you want, think of it as a cosmetic trick, nothing more. Great, so the next step is to implement sum for each branch of the match. If it is nil, then the sum is 0. Otherwise, we call sum recursively on the tail of the list and then add the number from the head, which keep it simple and clear. It also works for small lists. However, if we call sum on a list of 10,000 elements, then boom, we have a Stack Overflow exception. So as you can see, this is a realistic concern. A Stack Overflow can easily happen when we implement recursive functions over lists. So does this mean we shouldn't use recursions whenever we work with lists? Again, not necessarily. There is one final technique I would like to share with you that ensures that some recursions use a constant amount of memory. Let's have a look at another example. Say we recursively implement contains, a function that checks if a number is present in a list. When the list is empty, we return false. And if not, we have a head and a tail. So we can compare the head with the number we are looking for. If they are equal, we return true. And if not, we call contain on the tail to recursively check each number in the list. Does that make sense? So we can try to call contains with a small list. And it seems to work perfectly well. We can even call contains with a large list as long as the target number is present toward the beginning, because if that's the case, the recursion will stop early. Now, what's really surprising is that contains also works on a large list even when the target number is not found. This doesn't make sense because in that situation, contains will call itself recursively a large number of times, and we might have expected this to trigger a Stack Overflow. However, despite the large number of calls made, if we compare contains and sum carefully, we'll notice a difference in the way the recursive calls are made. Contains calls itself as a last step of the function, while for sum it needs to execute plus head after the recursive call. This may seem like a tiny difference, but it has a profound impact on the stack safety of this function. When a recursive function ends with a recursive call and nothing is done with the result, we said the function is tail recursive. In that case, the compiler can rewrite it using a loop, which means that we are entirely safe and there will be no possibility of a Stack Overflow exception. Now, you might wonder what happens if we change sum so that it ends with head plus instead of plus head. Will that make sum tail recursive? No, it doesn't. In both cases, sum will throw an exception on large inputs. This is confusing because plus is an infix operator. But if we introduce a variable, then we can see that sum does not end with a recursive call. To be honest, this can be very difficult to spot. It took me several years before I was able to recognize whether a function was tail recursive or not. However, the good news is we don't need years of training because the compiler can check this for us. If we add a tail rec annotation before the method's definition, we'll see that contains is unaffected, but sum will now fail to compile. The error message doesn't help us to fix the problem, but at least we are aware there is one, which is a good start. It turns out that there is a technique to make sum tail recursive. To do so, we'll need to add an extra parameter in which to store the state of the computation. Every recursive step will increase this parameter. Then when we reach the end of the list, instead of returning 0, we would return the accumulated state. If you have never seen this technique before, it takes some time to get used to it. But if you think about it, the principle is the same as with the imperative implementation, except that instead of using a variable to store the state, we use an extra parameter. Now, if you were paying close attention, you might have noticed that we changed the signature of sum when we added this extra input. So to fix that, we could add an overloaded version of sum with the expected signature, and we'll delegate the implementation to the tail recursive version with state hard-coded to 0. And if you want to hide the tail recursive version, you can either make it private or define it as a nested method, whichever you prefer. If you want to practice writing that sort of stack-safe recursive function, I've added some optional exercises to the file stacksafe recursive exercises.scala. and you can find all the answers in the repository. So in conclusion, recursive functions are a great way to analyze recursive data structures, like trees, which are extremely common. However, recursive functions are potentially dangerous, as each recursive step consumes space on the stack, which is a very limited resource. And so today we have covered a few ways to sidestep this issue using data structures with limited depth, or the tail recursive optimization provided by the compiler. Now, even if it's possible to write stack-safe recursive functions, the real question is it desirable? As is often the case with programming, it depends. If we look at the tailrec implementation of sum, this code is neither clear nor concise, and it's error-prone because we can easily forget to check for stack safety. Loops and mutations do not fare well either, as we saw earlier when we traversed a file system to implement disk usage. That's why I would always recommend, whenever possible, to favor pre-built and well-tested iterator functions like fold left, instead of hand-rolling our own solutions based on loops or recursions. So I hope you enjoyed this video, and I will see you soon for the next one.